Okay, let's dive in. Look up at the sky, feel the wind. The air above us isn't just there, it's moving
Yeah, and
constantly.
always in motion.
And not randomly either. There's this incredible logic to it, driven by fundamental forces.
Absolutely.
So today's deep dive is all about unpacking that logic, why air moves, the vast invisible forces shaping its flow, the massive patterns it creates around the planet.
And how all of that translates into the weather we experience every single day, from like a gentle breeze to a monster storm.
Exactly. We've got a stack of material here focused on atmospheric circulation and weather systems.
Right. Think of this as maybe a shortcut to understanding the engine room of our atmosphere.
Yeah,
Our mission is to sort of cut through the complexity and get to the core concepts, showing you how something as simple as the weight of air can scale up
right.
to drive global patterns and generate the most violent storms on Earth.
We want to make sense of how it all connects and, crucially, why it matters to you, wherever you are listening. And we'll tackle some really intriguing questions along the way, like, well, if the air pressure above you is crushing down, why aren't there just perpetual, super strong upward winds everywhere?
Good question.
And how does the Earth's gentle spin end up bending winds into massive swirls?
Yeah, the Coriolis effect.
What's truly happening inside that eerie, calm eye of a hurricane? And how do boundaries between different air types create those dramatic weather fronts?
All fascinating questions, and they're all driven by the dynamics of the atmosphere. So let's start with the most fundamental concept. The air itself actually has weight.
The weight of air, that's atmospheric pressure, right?
Precisely. Atmospheric pressure is the weight of the entire column of air directly above a given area, from the surface all the way to the top of the atmosphere. Imagine stacking up all those air molecules. That's the weight.
And we measure that weight in millibars, or
Mhm.
dim, and at sea level, the average is about, what, 1,013.2 millibars? That sounds like a lot of weight.
It is. It really is. And because gravity is pulling that air down, the air near the surface is compressed, it's denser. Right. Which means the pressure is highest at low altitudes, like sea level.
Okay, so if pressure is highest at the bottom because all the air is pressing down, doesn't that mean there's this massive pressure difference vertically, just pushing air up? Like really hard.
That's a fantastic question, and you've hit on a key insight there. The vertical pressure gradient, for the force pushing air from high pressure near the surface towards lower pressure higher up, is actually much, much larger than the horizontal pressure differences that drive most of our winds. It's tremendous.
So why isn't air just constantly rocketing upwards everywhere? I feel like it should be.
Well, because that enormous upward pressure gradient force is almost perfectly balanced by an equally strong force pulling the air downwards, gravity.
Oh,
It's a
okay.
delicate, near-perfect balance happening all the time. We call it hydrostatic balance. That vertical balance is why we don't have constant, powerful updrafts.
Yeah,
It's only when that balance is slightly disturbed, maybe by heating or something else.
if we get vertical motion, like in a thunderstorm.
Exactly. So the huge vertical force is mostly canceled out by gravity. But even tiny differences in horizontal pressure, side to side, are super important for wind.
They're the main driver then.
They're the primary driver of horizontal air movement, yeah. Even small horizontal pressure differences can cause air to flow. And we visualize these patterns on weather maps using isobars.
Isobars, those are the lines connecting points of equal pressure.
That's right. And to draw these maps accurately, especially comparing places at different altitudes, all the pressure measurements are adjusted as if they were taken at sea level. It levels the playing field, so to speak.
Got it. So tight isobars mean a strong horizontal pressure difference, like a steep hill for air.
Exactly.
And loosely spaced ones mean a weak difference, a gentle slope.
You got it. The closer the isobars, the stronger the pressure gradient force pushing the air, and the faster the potential wind speed. On these maps, you'll see areas where the isobars form closed circles. Those are low-pressure systems, sometimes called cyclones.
Lowest pressure in the center.
Right. And high-pressure systems, or anticyclones, with the highest pressure in the center.
And these pressure patterns aren't just isolated blobs. They tend to form these large-scale belts around the globe, don't they?
They do, yeah. There's a general sort of idealized pattern of global pressure belts. You generally find low pressure near the equator.
The equatorial low.
Right. Then high pressure around 30 degrees north and south, the subtropical highs. Then low pressure again around 60 degrees, the subpolar lows. And finally, high pressure near the poles, the polar highs.
And these belts, they shift a bit with the seasons, following the sun.
Yes, they aren't perfectly static. They migrate seasonally, following the sun's apparent movement. They shift poleward in the summer hemisphere and equatorward in the winter hemisphere. And this seasonal oscillation has a really big impact on regional weather patterns, like where the deserts are, where the rainy zones are.
Okay, so pressure differences create the initial push, that's the pressure gradient force, high to low. But wind doesn't just go straight from high to low, does it? Because the Earth is spinning. That messes things up, or changes things, rather.
Absolutely does. It doesn't mess them up, it organizes them. Horizontal wind near the surface is shaped by the interplay of three main forces. The pressure gradient force, which is the initial driver from high to low.
The starter motor.
Yeah, good analogy. Then there's the frictional force, which opposes the motion, acting like drag.
Makes sense.
And the Coriolis force.
Friction, that's just air dragging along the ground, or trees, or buildings, or even the ocean surface, slows the wind down, strongest near the surface.
Correct. Its influence decreases pretty rapidly with height.
Right.
Typically, it's negligible above maybe 1 to 3 kilometers. And it's also less significant over smooth surfaces like the ocean compared to rough, hilly terrain.
Right. Now, the Coriolis force, this is the one that always feels a bit weird, counterintuitive. The Earth's just spinning. How does that bend the wind?
It's an apparent force, yeah.
Mm-hmm.
It's a consequence of observing motion from a rotating frame of reference, which is what we're doing, standing on the spinning Earth.
Okay.
Think about trying to roll a ball straight across a spinning merry-go-round. To you, standing off the merry-go-round, the ball goes straight. But to someone on the merry-go-round, the ball appears to curve because the ground beneath it is moving sideways.
Ah, okay. So
No.
it looks like it's deflecting from the perspective of the rotating surface.
Exactly. In the northern hemisphere, this apparent deflection is always to the right of the direction of motion. In the southern hemisphere, it's to the left.
And the effect is stronger for faster winds and stronger closer to the poles.
Precisely. The Coriolis force is proportional to the wind speed. Faster wind, more deflection. And it's also proportional to the sign of the latitude. So it's maximum at the poles and 0 right at the equator.
0 at the equator, that's really important, isn't it, for hurricanes?
It's crucial. Because there's no Coriolis force right at the equator, tropical low-pressure systems can't develop the strong, organized spin needed to become hurricanes or typhoons. They need to be a few degrees away from the equator for the Coriolis force to kick in and get them spinning.
Fascinating. And this force, it acts perpendicular to the wind's motion.
Yes, the pressure gradient force pushes air across isobars from high to low. The Coriolis force acts at a right angle to the direction the air is actually moving.
Okay.
Now, when these two forces, pressure gradient and Coriolis, balance each other out, which happens mainly in the upper atmosphere where friction isn't really a factor,
Right, above that 1-3-kilometer layer.
you get what's called the geostrophic wind.
Geostrophic wind, is that the one where the wind blows parallel to straight isobars, not across them?
It's the one. At about 2-3 kilometers up, friction is negligible. The pressure gradient force pulling air towards low pressure is perfectly balanced by the Coriolis force deflecting it. The net result, wind flows along the isobars, not across them.
But near the surface, friction messes with that balance.
It does. Friction slows the wind down. Slower wind means less Coriolis deflection. So the pressure gradient force wins out slightly, causing the wind near the surface to cross the isobars at a slight angle, spiraling towards lower pressure.
And this combination of pressure gradient, Coriolis, and friction explains why winds swirl around high and low pressure systems differently in the northern and southern hemispheres.
Exactly. Because the Coriolis deflection is to the right in the north and left in the south, air flowing into low pressure systems gets deflected.
So it spins anti-clockwise in the northern hemisphere.
Correct.
And clockwise in the southern hemisphere, like water down a drain, but opposite in the south.
Kind of, yeah. And conversely, air flowing out of high-pressure systems gets deflected, making it spin clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere.
And this horizontal flow, the converging into lows and diverging out of highs, has a massive impact on whether we get clouds and rain or clear skies.
It's absolutely fundamental. Where air converges horizontally at the surface, like in a low-pressure system, well, it has nowhere to go but up.
Right, piles up and rises.
And rising air cools, condenses water vapor, forms clouds, and often leads to precipitation.
So lows generally mean bad weather.
Often, yes.
Yeah.
Conversely, where air diverges horizontally at the surface, like under a high-pressure system, air from above has to sink down to replace it.
Sinking air, that warms up, right?
It does. Subsiding air warms as it gets compressed, which evaporates moisture and inhibits cloud formation. So high pressure usually means fair, stable weather, clear skies.
Okay, that ties it together nicely. Pressure differences create the force, Earth's spin bends the flow, friction slows it near the ground, and the resulting swirl directs air up for clouds or down for clear skies. Now let's zoom out again to the really big picture, the general circulation of the atmosphere. These are the planet-wide wind patterns.
Right. The general circulation is basically the average pattern of winds across the globe. It's shaped by everything we've just discussed, but operating on a planetary scale. Think about the uneven heating between the equator and poles.
Yeah.
The tropics get way more sun. Those global pressure belts we mentioned, their seasonal shifts, the huge influence of land versus ocean distribution, and, of course, Earth's rotation and the Coriolis effect.
And there's a kind of simplified model for this, isn't there, with these big cells of air movement?
Yes, exactly. It helps visualize the large-scale flow. The most prominent one is the Hadley cell, which dominates the tropics.
Hadley cell. How does that work?
Well, intense solar heating near the equator causes air to warm up, become less dense, and rise vigorously. This happens in a zone called the Intertropical Convergence Zone, the ITCZ.
The ITCZ, that's that band of low pressure near the equator where the winds seem to converge from north and south. Lots of clouds and rain there usually.
That's the one. It's a zone of convergence and powerful rising air due to that strong thermal convection. This rising air then moves poleward, high up in the atmosphere, maybe 10, 15 kilometers up.
Okay, so it rises at the equator, moves north or south high up. Then what?
As it moves poleward, it cools and starts to sink back down around 30 degrees north and south latitude. This sinking air is what creates those belts of subtropical high pressure we talked about earlier.
Ah, okay. So the sinking air forms the highs around 30 degrees.
Right. And then, to complete the loop, at the surface, air flows from those subtropical highs back towards the equatorial low pressure of the ITCZ.
And those are the trade winds.
Yes, but they don't flow straight south or north. The Coriolis force deflects them, so they become the northeast trades in the northern hemisphere and the southeast trades in the southern hemisphere, generally blowing from the east or easterly. That whole loop rising at the ITCZ, poleward flow aloft, sinking at 30 degrees, and surface flow back to the equator as easterlies, that's the Hadley cell.
And it's basically a massive heat engine moving energy from the hot equator towards the poles.
Exactly. It's incredibly important for the Earth's energy balance.
And what about beyond the tropics? What happens in the mid-latitudes where most of us live?
In the mid-latitudes, roughly between 30 and 60 degrees, you have what's called the Ferrel cell. It's a bit more complex and less direct than the Hadley cell. It involves the interaction of the sinking air near 30 degrees and colder air moving down from the poles. The surface winds in this cell are predominantly from the west, the westerlies.
The westerlies, that's why most weather systems in places like North America and Europe move from west to east.
That's the primary reason, yes. Then, near the poles, you have the polar cell. Here, very cold, dense air subsides near the poles, creating the polar highs. This air then flows equatorward at the surface.
And gets deflected by Coriolis.
You bet. Deflected to become the polar easterlies.
So we have these three cells in each hemisphere, Hadley, Ferrel, Polar, all working together.
That's the general picture. They act as a giant conveyor belt system, transporting heat energy from the lower latitudes, where there's an energy surplus, towards the higher latitudes, where there's an energy deficit. It's the planet's way of trying to even out the temperature differences.
And this massive atmospheric circulation doesn't happen in isolation, right? It's constantly interacting with the oceans below.
Oh, the interaction is profound. They're completely coupled. Large-scale winds blowing over the ocean surface drive the major ocean currents, moving enormous amounts of water and the heat stored in that water around the planet.
And the ocean influences the atmosphere back.
Absolutely. The oceans store and release huge amounts of heat. They also provide the vast majority of the water vapor that fuels clouds and precipitation. So the ocean surface temperature and currents have a massive feedback effect on atmospheric circulation patterns.
And this interaction is especially clear in the Pacific Ocean with the whole ENSO phenomenon, El Nino and La Nina.
It is. ENSO, which stands for El Niño Southern Oscillation, is probably the most significant and well-known example of this coupled ocean-atmosphere interaction. El Niño specifically refers to the occasional significant warming of the surface waters in the central and eastern tropical Pacific.
Particularly off the coast of South America, like Ecuador and Peru, replacing the usual cold current there.
Exactly. That unusually warm water.
And the southern oscillation part is linked to the atmospheric pressure changes.
Yes, it refers to a large-scale seesaw in atmospheric pressure that occurs between the central eastern Pacific and the western Pacific Indonesia region. When pressure is high in the west, it tends to be low in the east, and vice versa. This pressure swing is tightly linked to the El Nino ocean warming. So ENSO is the term we use for the whole combined ocean-atmosphere phenomenon.
And the really striking thing is, when ENSO is strong, whether it's El Nino or La Nina, it doesn't just affect the weather in the Pacific. It has ripple effects across the entire globe.
That's the critical takeaway, yeah. Strong ENSO events can dramatically alter global atmospheric circulation, leading to major shifts in rainfall patterns and temperatures worldwide.
Like what kind of impacts?
Well, a strong El Niño, for instance, can bring heavy rains and flooding to the normally arid coastal regions of Peru and Ecuador,
Right.
while simultaneously causing severe droughts in places like Australia, Indonesia, parts of Africa, and sometimes impacting the Indian monsoon. It can influence hurricane seasons in the Atlantic, winter weather in North America. Its reach is truly global.
Which is why it's so important for long-range weather forecasting.
Absolutely. Predicting ENSO conditions is a key part of seasonal forecasting months in advance.
And La Nina is basically the opposite condition, colder water in the eastern Pacific.
Correct. La Nina features stronger than average trade winds piling up warm water in the western Pacific, leading to an abnormal accumulation of cold water upwelling in the central and eastern Pacific. It also has significant, often opposite global weather impacts compared to El Nino.
Okay, so we've got the huge global patterns and the ocean interactions, but air circulation also happens on much smaller, more local scales, right? Driven by maybe seasonal heating shifts or even just daily differences in how things warm up.
Yes, definitely. Those broad seasonal shifts in heating and the migration of the global pressure belts really modify the general circulation on a regional level. The most dramatic example is probably the monsoons.
Monsoons, like in Southeast Asia?
Exactly, where you get these massive seasonal reversals in wind direction, leading to distinct wet and dry seasons. That's a huge seasonal modification of the larger circulation.
And then there are even more local winds, like the ones you feel at the beach or maybe living near mountains.
Classic examples. Those are driven by what we call differential heating, different surfaces heating up and cooling down at different rates. Take the coast. During the day, land heats up much faster than the sea.
Right, sand gets hot quickly.
So the air over the land gets warmer, expands, becomes less dense, creating lower pressure over the land. The sea stays cooler, so the air above it is cooler, denser, higher pressure.
So the wind blows from the sea to the land.
Yep, the sea breeze, blowing from the relatively high pressure over the cool water towards the lower pressure over the warm land. Very common on sunny afternoons near the coast.
And then at night, it flips.
It reverses. Land cools down much faster than the sea once the sun goes down. Now the land is cooler, higher pressure, and the sea is relatively warmer, lower pressure.
So the wind blows from the land out to the sea, the land breeze.
Exactly. Same principle applies in mountainous areas. During the day, mountain slopes heat up faster than the valley floor. Air rises along the slopes, drawing air up from the valley. That's the valley breeze.
Upslope slope?
Right. Then at night, the slopes cool down rapidly. The air next to them becomes cold and dense and drains downslope into the valley. That's a mountain wind, or more generally a katabatic wind, any wind blowing downslope due to gravity acting on colder, denser air.
You can even get warm winds coming down the other side of mountains, right? After air has dropped its moisture going up one side.
Yes, that's adiabatic warming. As air is forced up a mountain, the windward side, it cools and often loses moisture as rain or snow. When that now drier air descends on the other side, the leeward side, it gets compressed by the increasing pressure.
And compression causes warming.
It does. So it warms up rapidly as it descends, often becoming significantly warmer and drier than the air at the same elevation on the windward side. Think of Chinook winds in North America or Foehn winds in Europe.
Okay. Speaking of different types of air, what happens when these large bodies of air with very different characteristics bump into each other? That's where we get into air masses and fronts, isn't it?
Exactly. An air mass is simply a huge body of air covering maybe thousands of square kilometers that has taken on relatively uniform temperature and humidity characteristics from the surface it's been sitting over.
So it acquires the properties of the ground or ocean beneath it.
Pretty much, yeah. The area where it forms needs to be fairly homogeneous, like a vast ocean surface or a large, flat continental area. We call that the source region. The air sits there long enough to pick up the local temperature and moisture properties.
And we classify them based on where they come from, like tropical or polar, and whether they formed over water, maritime, or land, continental.
That's the basic classification. So you get warm and moist maritime tropical air, MT, typically forming over warm oceans. hot and dry continental tropical CT from subtropical deserts, cold and moist maritime polar, MP, from high-latitude oceans, very cold and dry continental polar CP from cold land masses like Canada or Siberia, and sometimes even extremely cold, dry continental Arctic CA from over permanent ice fields.
So tropical means warm, polar or Arctic means cold, maritime means moist, continental means dry.
That's the gist of it. And these air masses don't stay put, they move, carrying those properties with them, influencing the weather in areas they travel over.
So what happens when, say, a cold, dry CP air mass from Canada runs into a warm, moist, MT air mass from the Gulf of Mexico?
That's where you get a front. A front is the boundary zone, the transition zone, between two different air masses. It's not usually a sharp line like on a weather map, but a zone where temperature, humidity, and wind change relatively rapidly over a short distance. The process of forming a front is called frontogenesis.
And this boundary zone is where most of the weather happens, right? The interesting stuff.
Precisely. Fronts are where the action is, especially in the middle latitudes where these different air masses frequently collide. Because the air masses have different densities, warm air is less dense than cold air. When they meet, the warmer air is typically forced to rise up over the colder air.
And rising air leads to
Clouds and precipitation. So fronts are associated with cloud development and often rain or snow. They also bring changes in temperature, wind shifts, and pressure changes as they pass.
We hear about different types of fronts on the weather forecast: cold fronts, warm fronts.
Yes, there are four main types based on how the air masses are moving relative to the boundary. A stationary front is when the boundary itself isn't moving much. The two air masses are essentially at a standstill.
Okay.
A cold front is where a colder, denser air mass is actively advancing and wedging underneath a warmer air mass, forcing the warm air up rapidly.
Often bring sharp showers, maybe thunderstorms.
Typically, yes. More intense, shorter duration precipitation often. Then there's a warm front, where warmer, less dense air is advancing and gently gliding up and over a retreating colder air mass.
More gradual lifting, so maybe steadier, lighter rain.
Often, yes. Layered clouds like stratus and more widespread, prolonged precipitation are common. Finally, there's an occluded front. This is a bit more complex. It usually forms when a faster-moving cold front catches up to and overtakes a warm front.
So it lifts the warm air completely off the ground.
Essentially, yes. The warm air gets sandwiched and lifted aloft between the advancing cold air and the cool air ahead of the original warm front. Occluded fronts often mark the mature stage of a low-pressure system.
And these fronts are fundamental components of the big storm systems we experience outside the tropics, the extratropical cyclones.
Absolutely. Extratropical cyclones, also called mid-latitude cyclones or depressions, are the large, sprawling, low-pressure systems that bring much of the significant weather to the middle and high latitudes. They almost always form along fronts, particularly the polar front, that boundary between cold polar air and warmer subtropical air.
How do they actually get started? What kicks them off?
Often it begins with a kink or wave developing on a stationary front. Maybe there's some disturbance in the upper atmosphere that helps initiate it. This causes the pressure to drop locally on the front.
Okay, a dip in pressure.
Right. And air starts to circulate around this low pressure. The flow pattern forces the warm air on one side to start moving poleward, becoming a warm front, and the cold air on the other side to start moving equatorward, becoming a cold front.
And that sets up the characteristic anti-clockwise spin in the northern hemisphere.
Exactly. The system starts to organize, developing distinct warm and cold fronts that spiral inwards towards the low-pressure center.
And they have a typical structure we might see on a weather map.
Yes, a very characteristic comma shape, often. You'll see a sector of warm air called a warm sector, nestled between the advancing cold front behind it and the retreating warm front ahead of it.
So warm air is trapped between the two fronts.
Sort of, yeah. Ahead of the warm front, that warm air is gliding gently up over the colder air, producing those widespread layered clouds and often steady precipitation. Behind the cold front, the advancing cold air is forcing the warm air in the warm sector upwards much more abruptly.
Leading to more convective clouds like cumulus or cumulonimbus showers.
Exactly. And typically, the cold front moves faster than the warm front.
So it catches up.
It usually does. When the cold front overtakes the warm front and lifts that warm sector air completely off the ground, you get the occluded front. This often represents the storm's peak intensity. After occlusion, the cyclone gradually weakens as its connection to the warm, moist surface air is cut off.
These sound quite different from the tropical cyclones, hurricanes, typhoons that we hear about causing devastation in the tropics.
They are fundamentally different beasts, yes. Key differences. Extratropical cyclones have those clear frontal systems: warm fronts, cold fronts, occluded fronts. Tropical cyclones have no fronts.
Okay, no fronts in a hurricane. What else?
Energy source. Extratropical cyclones get their energy primarily from the temperature contrast between the different air masses involved. Tropical cyclones derive their immense energy from the release of latent heat when water vapor condenses into clouds and rain, and that moisture comes from evaporating very warm ocean water.
So they need that warm ocean fuel.
Absolutely essential. Sea surface temperatures need to be above about 27 degrees Celsius, or 80 Fahrenheit. Other differences. Extratropical cyclones are generally much larger in area, but their maximum wind speeds are usually lower than in intense tropical cyclones. Extratropical cyclones can form over land or sea, while tropical cyclones form only over warm oceans. And their typical tracks are different. Mid-latitude cyclones usually move west to east with the westerlies, while tropical cyclones often move east to west initially with the trade winds.
And tropical cyclones, those are the really violent ones. Hurricanes in the Atlantic, typhoons in the western Pacific.
Cyclones in the Indian Ocean, willies off Australia. Yeah, different names for the same type of intense rotating storm originating over warm tropical waters. They bring large-scale destruction from incredibly strong winds, torrential rainfall, and often devastating storm surges.
What conditions do they need to form and get really strong?
Several key ingredients need to come together. First, that warm sea surface temperature over 27 degrees C, providing heat and moisture. Second, you need the Coriolis force to get the rotation going so they can't form right on the equator.
It needs to be at least 5 degrees or so away.
Generally, yes. Third, you need relatively small changes in wind speed and direction with height-low vertical wind shear. Strong shear can tear a developing storm apart.
Okay.
Fourth, often a pre-existing weather disturbance, like a weak low-pressure area or a tropical wave, helps get things started. And finally, you need divergence or spreading out of air high up in the atmosphere above the developing storm to help draw the rising air upwards.
And their energy, you said, comes from condensation.
Yes, the latent heat released when massive amounts of water vapor condense into the towering cumulonimbus clouds surrounding the center. It's like a giant heat engine running on moist, warm air. That's also why they weaken rapidly and dissipate when they move over land.
Because their fuel supply, the warm ocean water, is cut off.
Exactly. More if they move over colder water. We talk about landfall. That's the point where the center of the cyclone crosses the coast.
And their structure is quite unique, with that central eye.
Very distinct structure. A mature tropical cyclone is this intense vortex of spiraling winds rotating around a central point. The storm system itself can be huge, maybe 600 kilometers or more across in some cases. But the really intense part is closer to the center.
Which is maybe 150, 250 kilometers across?
Something like that for the core area. And right at the center, you have the eye.
The calm part.
Right. A region of relatively light winds, clear or partly cloudy skies, where air is actually slowly sinking.
Sinking air. In the middle of the most intense part of the storm, that still feels weird.
It is counterintuitive, but it's a key feature. Immediately surrounding this calm eye is the eye wall.
And that's the dangerous part.
That's the zone of maximum intensity, a ring of dense, towering thunderstorms where you have the strongest spiraling ascent of air, the highest wind speeds which can exceed 250 kilometers per hour in extreme cases, and the heaviest torrential rainfall.
Wow. And outside the eye wall.
You have spiral rain bands, which are other bands of thunderstorms and heavy rain that spiral outwards from the eye wall. The weather generally becomes less severe as you move further from the center.
They move pretty slowly across the ocean, don't they? Compared to how fast the winds are inside the storm.
Yes. Their forward speed is often quite slow, maybe 15-25 kilometers per hour or 300-500 kilometers per day, though this can vary a lot. Those that track poleward and then curve back towards the east around 20 or 30 degrees latitude can sometimes accelerate and often become particularly dangerous as they interact with mid-latitude weather systems.
And the storm surge is a huge threat, too.
A massive threat. The combination of low pressure and strong onshore winds can pile up seawater and push it onto the coast, causing extensive flooding in low-lying areas, often responsible for the majority of fatalities.
Okay, so we've covered the big cyclones. What about other severe but maybe more localized storms, like thunderstorms and tornadoes?
Right. These are generally much smaller in scale and shorter in duration than cyclones, but they can be incredibly violent.
Thunderstorms, they come from those big cumulonimbus clouds.
Exactly. They're basically intense, localized convection cells.
Mm-hmm.
They often form on hot, humid days when the surface heating is strong, causing air to rise rapidly and form those tall, puffy cumulonimbus clouds. They produce thunder and lightning, heavy rain.
And sometimes hail.
Yes. If the updrafts within the cloud are strong enough to carry raindrops high up into freezing levels multiple times, they can grow into hailstones. If there's not enough moisture available, the strong downdrafts associated with a thunderstorm can sometimes just kick up dust and create a dust storm.
They have that life cycle, right? Updrafts building the cloud, then downdrafts bringing the rain and cool air.
Yeah, the updraft dominates initially as the cloud grows, then downdrafts develop, often triggered by falling precipitation, leading to the mature stage with both up and down drafts, and eventually the downdraft cuts off the updraft, leading to dissipation.
And tornadoes, they're linked to thunderstorms too.
Yes, the most violent tornadoes form within the strongest type of thunderstorms, called supercells. A tornado is a violently rotating column of air that descends from the base of the thunderstorm, often visible as a funnel cloud extending towards the ground.
And they have incredibly low pressure at the center.
Extremely low pressure and incredibly fast rotating winds, causing massive destruction along their typically narrow path. They are most frequent in the middle latitudes, especially places like the central United States. A tornado that forms over water is called a waterspout.
So whether it's a gentle sea breeze, a globe-spanning circulation cell, a monsoon, or a terrifying tornado, it seems like it's all part of the atmosphere trying to balance things out, trying to redistribute energy.
Fundamentally, yes. All these phenomena, from the smallest local wind to the largest storm systems, are manifestations of the atmosphere trying to adjust to uneven heating and energy distribution across the planet. They are mechanisms for converting potential energy stored due to temperature differences or height and heat energy into kinetic energy, the energy of motion or wind. It's the atmosphere constantly seeking a state of equilibrium, ironing out those imbalances.
We've covered a massive amount of ground today. Wow. We started with just the simple idea of the weight of air creating pressure, then saw how forces like the pressure gradient, friction, and that really fascinating Coriolis effect shape how that air moves, from local breezes right up to the jet streams.
We looked at how those forces drive the huge global circulation cells, Hadley, Ferrel, Polar.
Yeah, and how that whole system interacts with the ocean, leading to things like ENSO, El Nino, and La Nina with their worldwide weather impacts.
And then how those atmospheric and oceanic interactions create the boundaries between different air masses, the fronts, which in turn fuel the development of weather systems, from the large mid-latitude cyclones that bring our day-to-day weather changes,
To the incredible focused energy of tropical cyclones, hurricanes, and those intense, violent local storms like thunderstorms and tornadoes.
we've really seen how seemingly simple concepts, like air having weight and the Earth spinning, scale up dramatically to create the complex, dynamic, and sometimes dangerous weather system that blankets our entire planet.
It really highlights how interconnected everything is, doesn't it? You know, the temperature of an ocean thousands of miles away can influence the rainfall here, or the simple daily heating of land versus sea creates a predictable wind you can almost set your watch by.
It does. Understanding these basics really helps pull back the curtain on the daily weather map and makes you appreciate the sheer power and intricate complexity of the air moving all around us.
It certainly does. It highlights the incredible forces constantly at play, forces often invisible to us until they manifest as, well, weather, sometimes beautiful, sometimes destructive. So here's something to think about. Considering the immense energy involved in all these systems, from the quiet, constant drama of air pressure balancing gravity, right up to the raw, terrifying, destructive power swirling inside a hurricane's eye wall, what does this constant motion, this relentless transfer of energy, really tell us about the ever-changing, restless nature of our planet's atmosphere? It's always searching for balance, isn't it? A powerful system to contemplate.